thank you guys for connecting to this new session of our research seminar. Today, I'm honored to introduce you Professor Anthony Wachs. Anthony is a professor in UBC, in the University of British Columbia in Canada. He holds a position in both the mathematics and chemistry engineering departments there. And well, Anthony is expert in the modeling and numerical simulation also of these complex fluids for saying in a general way. In my opinion, also the work of Anthony is really nice because he's succeeding this to have some work in this phase, let's say, connecting the mathematics and the engineering world. That this is really nice to see. So Anthony, thank you for accepting our invitation, and I give you the audience of our center.
Okay, wow, great. Thank you very much, Sergio. I'm delighted to be here today, and thanks everyone for taking the time to attend this talk. So yeah, so that's what I'm going to talk about, microstructure-informed models of hydrodynamic force and torque in a static random array of spheres. And I think that was already nicely introduced by Sergio. I think it's a good illustration of a connection between applied mathematics, scientific computing, and then physical analysis of a rather complex fluid mechanics problem. So as a general introduction, so let me try to see if I can move this somewhere. Yeah, here maybe, or we can do something like this. Yeah, okay, I'll put it here. Okay, so this is what in general my research group is interested in. So we're spanning a range of areas, going from granular flows, so just interactions through collision and gravity of rigid bodies, and essentially are interested in non-spherical shapes. Then the same when these particles are seated in a fluid around, and also ranging from rather a low Reynolds number flows to a pretty inertial flows, including sometimes the suspending fluid is non-Newtonian. So Sergio's been working a lot in the area of yield stress fields, and indeed we also have some interest in how particles move in the yield stress fields. So recently we also started to work on deformable capsules, and I'll show you a few recent results just for the fun of it. And mostly the application of these models are for red blood cells flowing in capillaries in the human body. And so to gain some additional physical understanding on these problems, we are developing and implementing numerical methods in a high performance computing fashion. We also have some different projects in that area. So we're not the spectrum, we're not computer science people. We really develop these methods and these models to gain physical understanding on the problem I talked about before. So before I dive into the topic of this seminar today, I just want to show you some sort of very nice and colorful movies about what we've done recently for granular flows and non-spherical particle and deformable caps, because I think that there's sort of just nice to see and to chat very quickly. I'm very happy to take questions about these two topics at the end of the talk. So how do we get insight in granular flows and non-spherical particles? And essentially recently we got interested in highly entangled particles. And so one of the standard flow configuration in the field of granular dynamics is just to create a pile of particles and see how it collapses, right? So it's just like an avalanche. And so how we do that, we do using a very well-known and widespread method in the literature called discrete element method. So basically you're resolving the contact between two colliding particles. So it's a particle scale model. And then the whole game is to be able to detect the contact or the collision between two non-spherical rigid bodies. So to do that, we're using an algorithm from the literature that dates actually from the mid-80s called the Gilbert-Johnson-Curtis. You might have heard about that, otherwise you can Google it. And it's essentially a shortest distance algorithm, okay? Everything is parallelized, and when we want to do non-convex bodies, we have a very, very naive approach, but efficient though, is that we're just gluing numerically convex bodies together to create a non-convex shape. So once we had implemented that model, we wanted to validate it and see what kind of additional physical insight we can get. And so we teamed up with an experimentalist. And the experimentalists ran many, many different experiments on again, the collapse of a pile or a column of cross-like particles. So why did we select cross-like particles? Because they're cheap. Because for anyone who's little handy with tools and goes to hardware stores sometimes over the weekend, you know that you can actually buy these crosses if you set new tiles in your bathroom or in your kitchen, because they're tile spacers, and they cost like $5 for 1,000 particles. So it's very cheap, and then you can run the experiment. So I'm just going to exit right now the slides because I was not able to include the movies in the slides. I don't know why. I'm going to show you what we get and what type of specific dynamics we get. So just moving out quickly, and I'll show the movies outside. So this is so let me see. This is an experiment. Okay, so you have this pile of particles here. You can recognize the tile spacers, and then we're going to open the gate. Okay, and so you can see how it collapses. It's very different from spheres. There's a first compaction phase, and then it's a top-driven. Okay, it's like a wave. Okay? It's a top-driven collapse. And so this is all driven by the microstructure of the pile and the shape of the particles. So the question was, can we reproduce that numerically? And so I'm going to show you a simulation right now. So this is exactly the same system. And you can see that the dynamics of the collapse is very, very similar to the experiments. So apparently we're capturing at least the order one dynamics in this flow. So the model is reasonably realistic. So now there was a second question that we wanted to answer, is that in the experiments, there's an initial aspect ratio of the pile or the column for which it doesn't collapse at all because it's too entangled. And we also wanted to see whether we can reproduce that. So these are two simulations, and then I'll comment on them later. I think they start that way. Okay, so that's just the column is a little wider and it's a little shorter, okay? And so this is a case where eventually we'll see collapse, okay? All right, it's very similar. There's a little bit of top driven. So now we created another system. Everything is the same except that the actual position of each particle in that pile is different. So it's a different microstructure. And see what happens with a different microstructure. Oh, sorry. It doesn't collapse at all. Okay, it stays completely stable. And that's because the particles are very much entangled, and so there's not enough mobility in the pile for the collapse to happen. And this has been seen in experiments as well. So there are aspect ratios for which sometimes you get a collapse, sometimes you don't get a collapse. And if you keep on changing the aspect ratio, you end up with some range of aspect ratios for which there's never ever a collapse. The pile is completely stable. So the good thing is that we were able to reproduce that with our particle scale model. And I think this was a nice result to show before really discussing the topic of the day. So let me go back to here. The other very short example of what we've been doing recently is for deformable capsules and the application to red blood cells flows in capillaries. So we've been building this numerical machinery that is a combination of a finite element solver for the deformation of the membrane that is essentially driven by elastic and bending forces with a Navier-Stokes solver. We're using immersed boundary when the deformable capsule moves on the grid. Okay, we're using embedded boundary for the walls of the capillaries, using STL files so we can have something pretty complex. And everything is implemented on octree grids. So we can do a dynamic adaptive mesh refinement. And I want to do a little bit of advertisement here. We're using an open source software called Basilisk. developed by a colleague of mine in Paris that has a huge community. And so if you have any interest in doing this type of simulation down there with adaptive octree refinement, I really recommend you consider Basilisk, because there's a already implemented Navier-Stokes solver to do that. You just have to implement your own models. So having that in mind, this is a type of simulation we can run. So these are two capsules. The top movie is a simple shear flow, okay, and it's just going to cross each other. And the bottom movie is just a capsule going through a contraction. And you can see very well the dynamic adaptation when the capsule moves and deforms in the flow. So this is all parallelized. It's all 3D, of course. I'm showing 2D movies, but this is all 3D. And now we have this numerical machinery, and we'll start to look at more physical problems and maybe help to address questions in, I don't know yet exactly what questions. We're probably going to team up with medical doctors, etc., and see whether we can help to understand the dynamics of blood flows in the human body. So these are very recent results that I wanted to share. So really, if you want to do octree adaptation, think about Basilisk. It's open source and it's free. Okay, so now I'm just going to stop that. So what I want to talk about quickly today is now particle-laden flows. The particles are rigid bodies, okay? They don't deform. There's been a sustained effort in a multi-phase flow community for the last 30, 40, 50 years to understand the dynamics of these particle-laden flows. So they're everywhere. You can think about sediment transport in river. You can think about atmospheric pollution. You can think about chemical engineering equipments. And this is an example. This is an equipment in a refinery, so oil cracking, essentially. And so you have these very nice particle-laden flow here. So there's an imposed flow upwards. The particle is heavier, so they also go downwards. And I'm just going to show the movie and explain what it is about. So you have a lot of clustering, these pretty high Reynolds number flows. And the interesting point here is that the large-scale dynamics that you see are actually driven by the small-scale dynamics. So when you zoom in, and you zoom in again, eventually you see each individual particles, okay, that have an average motion, but they also have some randomness on the top, all right? That comes from the fluid around, that comes from the collisions. And then you can understand that to understand the large scale dynamics, you also need to understand the small scale dynamics because there's no separation of scales, okay? So when you zoom out again, and you again can tell yourself that this large scale dynamics and clustering is driven by the small scale dynamics. So when you have this in mind, oops, sorry. When you have this in mind, what the community has been doing over the years is to try to develop different models for these particle-laden flows at the different scales. So in terms of fluid mechanics only, there have been three types of models proposed in the literature. Models that resolve the kinematics around each particle, so microscale models. They're called Euler-Lagrange. So the Lagrangian phase is the dispersed particles, the Eulerian phase is the fluid. And so you're basically calculating the fluid flow around each individual rigid body. Okay, so this is very accurate. However, it's extremely computationally expensive. And so you can consider a large number of particles. Then at the end of the spectrum, you can see the dispersed phase as a pseudo-continuum fluid, so another fluid if you want. And you can write models that are called Euler-Euler because you're describing the two phases in an Eulerian fashion, okay? So you need a lot of closure laws here to make these models work. And somewhere in between, you can still track the particles individually, but you solve the fluid equation, the fluid conservation equation in an average fashion, okay? So you have this hierarchy of models, microscale, mesoscale, macroscale. And of course, when you go up the scales, you need more and more closures to close your models because you're sort of averaging things. And so you need to provide, again, some closure for the average terms. So the logic would be, this is supposed to be the reference solution because I'm just solving basic conservation principles. Okay, so there's no assumption here. It's just a Dirichlet boundary condition. It's just no slip on the surface of the particle. This is very elementary, but this costs a lot. But what I can learn from here, I can transfer it to the upper scale, mesoscale, to close to close the terms that need to be closed. And what I learned from the mesoscale, I can use it to close the additional terms that need closure at the macro scale. So there's this game of trying to transfer the knowledge you learn from the lower scale to the larger scale, okay? And so what I want to talk about today is one specific term that needs closure. And when you move from the micro scale to the mesoscale, you can see that your cells, okay, your finite volume cells, your finite elements, whatever, they're much bigger right now at the mesoscale than the individual particles. And so obviously you cannot get the detailed kinematics around each rigid body, and you cannot get the hydrodynamic force and torque just by integrating, because you don't have the proper values. So one term that needs closure is the interface momentum transfer, and essentially that means the hydrodynamic force and torque exerted on each particle. So the question is, when I compute the flow at the micro scale, I have exactly the hydrodynamic force and torque on each individual particle, and provided my computation is converged in space, I have the right value. So how do I construct a model that gives me the hydrodynamic force and torque on the particles at the mesoscale? Okay, so that's really the objective. So the usual workflow, right? It's very naive what I say here. I mean, you do data collection, then you do data analysis, and you try to design your model, and then you test your model. Okay, it's very standard. So what I want to talk about today is two of these different phases in this workflow, different steps, is data collection at the end of the talk. But right now I'm going to spend the next 20 minutes talking about designing the model. And essentially designing two types of models, a stochastic model and two microstructure-informed deterministic model. So what is actually the problem? All right, so I'm going to spend 1-2 minutes here. So you take a very small control volume and you seed it with particles. And to simplify, we're going to assume that the particles don't move and there's an imposed flow. So this like flows through a porous medium. What we know in the literature, in such a configuration, we know what is the average hydrodynamic force exerted on this particle. Okay, so you do a microscale simulation, you have all the different forces, you take the average, and you can design a law, okay, a law here that depends on the Reynolds number, so how fast is the flow, and on the volume fraction. And then you have these extremely complicated laws available in the literature. There are these 10 different. Well, don't ask me why. They're all supposed to do the same, okay? But the important part is that if right now you plot the average, you plot the individual force, so the force exerted on each individual particle, you get a lot of scattering around the mean, okay? So the level of scattering, the fluctuations, here fluctuations are between -2.5 and 2.5 roughly, and the average force is 5. So you have an amplitude of fluctuation of 5 for an average of 5. So you have as much fluctuation as average. So now the problem is, can I design a model that recovers the fluctuations as well? Not only the mean value, not only the average, but also the fluctuations, okay? And that's an open question in the literature, and people are starting to try to answer this question, okay? So there's basically a strong correlation between, again, the average volume fraction, the average Reynolds number, and the average force. But there's no correlation between the local force and the local volume fraction, or the local force and the local Reynolds number, okay? So the objective is to recover these fluctuations. And it's pretty easy to understand why it's fluctuating so much. So these are 4 very naive pictures. Okay, so that's a control volume, 4 particles. I'm interested in the hydrodynamic force and torque exerted on the green particle. So if I impose a given flow, okay, I'm going to have a given average Reynolds number in that control volume, and it's the same in the 4 pictures. And I'm going to get an average volume fraction. And it's again the same in these 4 pictures because I have exactly the same number of particles, right? But you can easily see, without being an expert in fluid mechanics, that the force exerted on the green particle in these 4 different configurations of the particle, so different microstructure, will be different. Clearly, there'll be a lot of so in these 4 pictures here, the standard model, so these laws are going to predict exactly the same value because they're only based on average, if you want average velocity and average volume fraction. But you know very well that the actual force on the green particle in these 4 configurations is completely different. And that's, again, it's what we have here in this scattering of data. So can we design a model that recovers the fluctuation? So we have to incorporate somehow the position of the other particles. Okay, we have to incorporate the position of the neighbors if we want to be able to recover the right force, because these different neighbors at their position are creating different disturbances in the flow. Okay, and so that's the objective of the talk. So the general principle design, and I write here things down for the drag, for the hydrodynamic force in the streamwise direction, but I can write it for the torque, I can write it for the lift. It's just the general design principle. I'm going to construct the actual hydrodynamic force as the average plus a deviation. Okay, it's pretty standard. And so I already know the average from these very well-known closure laws that I showed before. And so now I need a model that can give me the deviation. Okay, so I can do that for the force itself. I can do that for the dimensionless force, in other words, the drag coefficient or the lift coefficient. Okay, it's pretty much the same. So an interesting thing, after I said that, again, the objective is to get the fluctuation, but amusingly, I'm going back here, all these different laws here for the average don't even agree with each other in the literature. So it's quite amusing, and they depart from each other, especially when the Reynolds number increases. So the more inertial the flow becomes, and the more they depart from each other. So we don't even agree on the average, but still we're trying to capture the fluctuation. So that's sort of an amusing comment. So maybe someone has to look at this problem as well. I'll talk about that at the end. All right, anyway, let's discuss the fluctuation. So I'm going to discuss 3 types of models. The first one is stochastic. So I'm not really using exactly the position of the neighbors. I'm not using the exact microstructure, but I'm trying to recover the fluctuation in a slightly different way. And I'll say a few words about that. The 2 other microstructure-informed models that I really want to talk about today are constructed in that form. So what's interesting here is to see that the fluctuation for the force or the torque, so there's no mean torque here because in this simple system, the mean torque is 0, okay, just by symmetry arguments, all right? So what's important here is that I'm going to take as additional parameters the positions of the m closest neighboring particles, okay? So I have my target particle, I'm going to take the local microstructure described by the position of the neighbors. And this is what I use as additional information to try to recover the fluctuations. All right. So a few words about the stochastic model first. So this is another interesting plot, and it's a key plot, is that if I take a Reynolds number, okay, and if I take a volume fraction, again, I showed that before, I'm not getting a unique value of the force, I'm getting a distribution of the force that I can plot as a probability density function, as a PDF, okay. So now the question is, can I recover that PDF? And I'm going to try to recover that with something that is stochastic. So essentially, I'm going to randomly select values around the mean and see whether I can recover the right dynamics. So this is something we did a few years ago. It was already proposed in the literature in 2005. And so I want to show you how the model is designed. So again, the idea, so here we only did it for the drag, for the streamwise direction, okay, for the drag force, but you can extend that to any force, I mean, lift and again, torque. And the construction is the same, an average value plus a fluctuation. And so the fluctuation is a first order autoregressive signal. It's an Ornstein-Uhlenbeck process. So there's a bit of memory in the signal here that depends on the parameter A. And there's a bit of randomness through a Gaussian white noise with an amplitude controlled by the parameter B. Okay, so that's a conceptual model, right? And the question is now, can I determine A and B? And the way we did that is that we computed the flow at the microscale that we assume to be the reference solution. We computed the flow at the mesoscale with this type of model, and we did a direct comparison between the results of the computation, and that's how we determine the magnitude of A and B. So A, for instance, we can say a few words about it. It's a memory, okay? It's a memory of the signal. So you can use the autocorrelation of the force and see how much the force is correlated over time. And there's, of course, it's going to be less and less correlated over the time. So you have a decay, okay, of the autocorrelation function. And you can take the characteristic time scale of the decay of the autocorrelation to determine the magnitude of the parameter A, okay? And the parameter B, you can also get it from the variance or the standard deviation of the PDF of the force. So to summarize, these two parameters A and B are not just tuning parameters. We can actually determine their value by computing the flow at a lower scale, which means at the micro scale. And so now the question is, are you getting any improvement when you do that? Are you getting any improvement of the predictions of the mesoscale model compared to a standard model that only has the average value? So we tested that in very simple configuration. So that's just a fluidized bed. So basically you have a bed of particle and you impose a flow from below, and then it starts to sort of oscillate around. And so on these plots, what you want to see is that blue and red are the standard model without the stochastic term. Black is the reference solution, is the microscale solution. Okay, so that's the particle result solution. And green is the improved model. And you can see that for all the different Reynolds numbers, we consider there's always a notable, a visible improvement of the predictions of the model when we're incorporating the stochastic component, so the fluctuating component of the hydrodynamic force. Okay, so apparently this is a model that's promising and that can deliver reasonably good results. All right, so now I want to talk about the two microstructure-informed models. All right, so the first model is what we call the probability-driven model, and the starting point is to answer the following question. What does the probability of finding a neighboring particle, okay, when the force and torque is lower or larger than the average value? In other words, you take a particle, right? You know the average force, now you put a neighbor somewhere, and depending on the position of the neighbor around this target particle, the force will be larger or lower, because that depends on the flow disturbance. So if you look at the probability and you don't constrain anything, you just say, what's the probability of finding a neighbor around the target particle? Well, you got something that's isotropic, right? It's just a geometric problem, right? It's not interesting. Now, what's far more interesting is when you say, where is the first neighbor when the force exerted on this target particle is larger than the average? In other words, the fluctuation or the deviation is positive. And then you get a probability map like this. And what's the probability of finding a neighbor when the force is lower? And then you get a probability map like this. These probability maps are three-dimensional, but I just squeeze them on the plane such that I can actually show them. Okay. So here, if you look at this one, again, it's very easy to interpret. If I have a particle at the front, upstream my target particle, I know that the hydrodynamic force exerted on the target particle will be lower. Again, it's the drag reduction effect. Okay, you're biking behind a track, it's much easier to bike. because there's less flow resistance on you. So that's basically what this probability map is telling you. So once you have done this analysis of the data, the question is, can you construct a model with that knowledge? And this is what we did. And sorry, I just want to say you can, of course, do that as well for the transverse force, for the lift. You can do that for the torque. And you always end up with the same type of probability maps, okay, qualitatively. So now I want to use these probability maps to try to predict the fluctuation, okay? So these are the model assumptions. So the first assumption is what we call superposition of pairwise hydrodynamic interaction. What does that mean? It means that I have one target particle, I have a number of neighbors around. I'm not able to construct a model when I take the effect of all particles at the same time. I just don't know how to do that. So what I'll do, I'll take one neighbor, I sort of estimate the fluctuation, I take another neighbor, I estimate the fluctuation, and then I sum these fluctuations. Okay, so I consider the interactions pairwise, only by two particles, and then I sum all the perturbations. If my flow would be 0 Reynolds number, that would be true, because the Stokes equations are linear. So I would be able to sum all the disturbances. Unfortunately, here I'm interested in non-zero Reynolds number flows. So I'm making an assumption of linearity, or I can sum things, but I have a non-linear problem. So I can already tell that at some point, this assumption is going to break down. But still, let's see what we can do. The probability maps that I can draw for each neighbor, I can eventually combine them in the single probability maps. But that's a little technical. I don't want to say too many things about that. Let's look at the model itself. So the model is constructed that way. So essentially, I'm going to consider a certain number of neighbors, and tests have shown that with 20 neighbors, I'm good. I don't have to use more neighbors than 20. 20 is enough to describe the local microstructure. So I'm going to use 20 neighbors, and I'm going to sum the probabilities, so the disturbances, and multiply them with a coefficient. So that's just it's a linear model, just summing things, okay? You can see again the pairwise hydrodynamic interaction. All the probability for the force to be lower than the average, all the probability for the force to be larger than the average multiplied by a coefficient. And everything is linear with these coefficients. The good news is that because everything is linear with the coefficients, I can get their value simply by standard linear regression. Okay, so I just do linear regression of that model with respect to the data, and I can determine the two coefficients here. All right, so these are the results. How much of the fluctuations or the deviations can I predict with that model? And I'm gonna I'll assess that by computing the coefficient of determination. Okay, so the model with respect to the real data. And so the good news is that I can predict up to around 85% of the fluctuation of the deviations, down to about 40–50%. All right. So, okay. So of course, 40–50%, we're not overly happy about it, but let's keep in mind that the standard models in the literature, they're predicting 0, because they're only predicting an average value. So if you can predict already 40–50% of the deviations, that's not too bad. And we can go up to 85%, which is pretty satisfactory. So now again, when we look at this array of numbers, it's very, very clear to see that one assumption or the model's predictions deteriorate when the Reynolds number increases and when the volume fraction increases. In other words, the more nonlinear the problem is, okay, the weaker the model is in predicting the right values, because I'm breaking this linear assumption that I made in constructing the models. So I cannot expect miracles, okay? While it's not too nonlinear, it's gonna work very well. When it's very nonlinear, I know that these are the limitations of the model, and so I'm not surprised to see these numbers. But anyway, on average, we can predict around 70–75%, or let's say 70% of the deviations, which is better than 0. So the second type of model is sort of very similar. So you know, a lot of people are excited these days by machine learning, neural network, etc., etc. I'm somewhere in between. I'm very cautious, and I'm trying to see how we can actually use some of these new approaches, but in a sort of in a controlled way. Created a physics-informed neural network, and the assumptions are very much the same. So we're still using superposition of pairwise hydrodynamic interaction, and this is an important point. So that's why I'm saying I'm very careful with neural networks. But someone might disagree with me and might be in love with neural networks. I don't know. So the first thing we did is we tried what we call a fully connected neural network. So basically, you take the data, you give that to a neural network, and the neural network gives you a number at the end. Okay, and of course, the neural network is completely blind to what the data are about. Okay, it's just data. Neural network don't know anything about what is the physical meaning of the data. So of course, it doesn't work very well because you need a large amount of data to train the neural network, for the neural network to work properly. And of course, we have limited data because we have to produce this data through particle resolve computations. They're very expensive. So now what you can do is that you can help the neural network to predict something sensible. And you can force the neural network to understand the data because you understand the data already. So now you have a physics-informed neural network. You're informing the neural network that there are additional principles that it has to satisfy, like symmetry principles, solving or satisfying conservation equation, etc., etc. So that's what we tried, a fully connected versus physics-informed. And the third assumption is the same. We only use about 20 neighbors, okay, to describe the microstructure, and we added symmetry assumptions to the model. So these symmetry assumptions belong to the category of informing the neural network to satisfy these things that the neural network doesn't really know. Okay, but in summary, the assumptions are very similar to the microstructure, the probability map model I presented before, except that instead of using linear regression and probability maps, now we're going to ask a neural network to do the job. So these are the symmetry assumptions we added to the model. This is a more recent work. So when we did the probability driven, we could have done that too, but we just didn't think about it. So when you look at the disturbance of the flow, you can see that the neighboring particle, clearly the disturbance for the force can only be in the streamwise direction, so EX, and in the transverse direction EL. For symmetry reason, you cannot have any disturbance in the direction ET. It's impossible, okay, because these are spheres. And for the torque, you can see that the only disturbance you're getting in this case is ET, also in the ET direction, also for symmetry assumptions, okay, symmetry properties. So this is what the physics-informed neural network looks like. So what we do is we create a fully connected neural network per neighbor, and then we sum everything at the end. So we're still using this pairwise hydrodynamic interaction assumption. We're still summing things at the end. Okay, and we're using a projection step to incorporate these symmetry assumptions I talked about. All right, so a very smart PhD student of mine implemented that. That's reasonably fast to do with all the online free libraries that exist to do neural networks right now. And this is the result. Okay, so again, we use the same test cases, and on average, we're predicting roughly the same as with the probability map driven model I showed before. Numbers are slightly higher, but it's not a substantial improvement. We're still predicting somewhere between 52%, it's the lowest, up to 90%. So before we were between 38% and 85%, now we're between 52 and 89. I don't think this is a major difference. But we again have the same effect that was predictable. The model performance decreases when the nonlinearity in the problem increases. So again, when the Reynolds number increases and when the volume fraction increases. So these models have the same drawback, is that they are built on a pairwise hydrodynamic interaction assumption. In other words, I'm summing the disturbances of each neighbor separately. Okay, so you can't expect anything magic. Again, it's not because you're doing a neural network that eventually the model is going to perform better. It's because there are physical assumptions that you use to construct the model. The other interesting thing is to really look at the performance between a fully connected, so the completely blind, naive neural network that you just throw data at it and you get a number, versus the physics informed, especially in terms of number of neighbors. So you may think that when you increase the number of neighbors in the model around the target particle, you are improving the description, okay, of the microstructure around that target particle. And so that's very logical from a physical point of view. You think I'm using more neighbors, the model will improve in terms of performance. Well, that's true for the physics-informed model. That's absolutely not true for the fully connected. And you can see that after 5 neighbors, the fully connected model just constantly predicts something worse and worse. And that's basically because we don't have enough data. Okay, again, these data are coming from particle result simulations that need millions of computing hours on large supercomputers. So we don't have enough data. So we can't do fully connected. And that's sort of proof that we are a long way from just throwing data at neural networks and just getting the right value in very nonlinear problems, such as the ones we're interested in fluid mechanics. So I don't think that's going to happen anytime soon. So there's a difference between the limitations of the two models. The fully connected model, the limitation is just practical. It's just scarcity of data. Okay, if you give me 1 billion computing hours on the largest supercomputer in the world, I can generate enough data, give it to the fully connected neural network, and it's going to perform very well. The physics informed, it's a theoretical limitation. Okay, it's a model design. It's this pairwise interaction assumption that's limiting the performance of the model. So what can we do to fix that if we want to try to improve even further these two microstructure-informed? Well, again, in terms of design, you can think about including a ternary hydrodynamic interaction. So instead of using a pair of particles, you're using 3 particles. So you have the target particle, the first neighbor, and the other neighbor. Okay, and so that's a second order correction to the model. So you can try to do that. I have a colleague at the University of Florida who's been working on that. There should be a paper out very soon about this, that there's further improvement if you use ternary hydrodynamic interactions. Computing reasons, scarcity of data is basically you need faster solvers or larger supercomputers or both to generate more data. So back to the question of data collection and faster solvers, and there are 2 potential gaps in the literature. So back to the question of the average force. Why do we disagree on the average force? I mean, so you have all these works published in the literature, and they absolutely don't predict the same. And you can see that the deviation is pretty large. So for a Reynolds number of 150, one correlation predicts 8, the other correlation predicts 12. Okay, that's a 50% difference. So what could be the reasons for that? Some of these simulations are not spatially converged. So people were a little casual in the way they run their simulations. I don't know. We haven't cross-compared all these different methods. Okay, so in the different methods, you have lattice Boltzmann, you have immersed boundary, or sometimes combined, a fictitious domain, embedded boundary cut cell method. So you have a variety of methods, and maybe they haven't been cross-compared yet, or we don't have enough data to construct even the correlations for the average value. I don't know. I'm just speculating, but I do want to answer that question at some point in the future. So how do you develop more accurate particle resolve direct numerical simulation solvers? No, we've been doing that again on octree. So we're using adaptive mesh refinement to capture the boundary layers better. And we, again, been implementing that in that solver that I really recommend you check at the end of this talk if you have any interest in this type of computations. And so these are the different models we're implementing on this platform. Distributed Lagrange multiplier, which is a method I've been using for 20 years right now, but never on octree grids. A lattice Boltzmann method on octree grids, and the conservative cut cell method on octree grids. So we have a lot of different solvers, and we can even start to try to compare their predictions within our group. We don't have to ask anyone else. That's probably something we'll do in the future. The other thing we've been working on is on fast solvers. So interestingly, The usual way of solving the Navier-Stokes equation on a Cartesian fixed structure, a fixed grid, is that you use a projection algorithm. So basically, you do a velocity prediction that doesn't satisfy mass conservation, so it doesn't satisfy divergence of the velocity is equal to 0, and then you project that by solving a Poisson problem for the pressure. Okay, so that's very standard. And of course, the Poisson problem is three-dimensional, and that's generally what costs you a lot, because it's not highly diagonally dominant, and et cetera, so you spend a lot of time solving the Poisson problem in 3D for large problems. So in 2011, Peter Mineff from University of Calgary and Jean-Luc Guermont from Texas A&M, they suggested a solver where you can replace the full Laplacian operator, the three-dimensional Laplacian operator, by a product of different operators in 1D. And when you do that, you can apply direction splitting even to the Poisson problem. So the good news is that once you do that, even if you solve a very big 3D problems, you only solve a sequence of 1D Laplacian problems. Okay, so it's super, super fast, and it scales very well with the number of cores. There's a little price to pay, of course, otherwise it would be too easy, because you're sort of trading the full 3D Laplacian operator for a product of 1D operators. Your velocity field is not exactly divergence. Okay, it's slightly non-divergence free, but you can control that with the time step magnitude. You can control that with the grid size, etc. So there are nice proofs in the original papers by Peter and Jean-Luc. So what can you do with that? Well, you can compute pretty large systems. So recently we have computed for one value of the Reynolds number and the volume fraction. We have computed the flow for about 150,000 spheres on 7 billion cells. And so that run on 7,000 cores. It only needs 2 days to reach the steady state, okay? And so now we have a lot of data to train our microstructure-informed models. Before, we were training them with maybe 2,000 or 3,000 spheres, okay, 2,000 or 3,000 data points. Now we can train them with 150,000 data points. So it's a complete game shifter. And you can see the scaling of the algorithm. The triangles are the scaling of the original projection method, and the circles is the scaling of this direction splitting solver. So at 5,000 cores, we still have a sort of a parallel efficiency of about 70–75%. Okay, so that's pretty nice. The current developments, we're trying to come up with a closed form of the probability-driven model. And so if you plot these different probability maps at different Reynolds number and different volume fraction, you can see that there's a continuous change. So if you want a prediction for any value of the Reynolds number and the volume fraction, the easiest thing you can do is you can interpolate. You can just interpolate these probability maps. And so we're trying piecewise linear interpolation. It seems to be working fine, okay? And you can also piecewise linearly interpolate the coefficients. So you can come up with a completely closed form, a closed form of the probability map model. So now you still have to interpolate probability maps. So you can do that in a discrete fashion, but what you can also do is you can try to reconstruct the probability maps with spherical harmonics, again, because of the symmetry properties in the flow. And that's another thing we've tried. So these are the probability maps extracted from the data, okay? And these are the probability maps that we reconstructed with spherical harmonics. And of course, you have coefficients that you have to determine. And again, you can use regression. And on average, for all the cases, that's an example for the fifth neighbor, the coefficient of determination for the reconstructed probability maps is above 95%. Okay, so the reconstructed probability maps represent very well the real probability maps from the data. So we can have a model that is based on spherical harmonics plus a set of coefficients that depend on the volume fraction and the Reynolds number, and we can come up with a closed form of the model, because that's something very important. Other people want to use the model, they want to implement it in their code. So if you can offer a completely closed form, it's much easier to implement. Otherwise, you need to publish the probability maps, and that's a little more complicated anyway. So yes, spherical harmonics are also very promising to reconstruct these probability maps. In conclusion, there's been quite an exciting piece of work done over the last 5 years on these models, and this was initiated by my colleague at the University of Florida, Balashender. I think that in the future, we're going to combine most likely machine learning models and physical insight. Again, I don't think we're at the point that we can use neural network in a blind fashion. And probably the improvement comes from ternary interactions. If you want more data, you can do GPU computing. I don't know much about GPU computing, so I put an interrogation mark here. What we're doing right now is using this direction splitting solver that is also a gateway for more data faster. And then no one has really tested this model, so no one has really implemented this model in the next scale, okay, in the mesoscale, and see how they perform. It would be interesting to see whether all the efforts we're putting in that field are eventually going to deliver something. So no one has tried that. That's something I want to do as well in my group. And then there are these two largely open questions. Is that we've been talking only about flows through a porous media, right? So we're talking about the flow where the particles are fixed, and there's a flow through this porous media created by the particles. But we are interested in dynamic particle-laden flows. Okay, so in a real particle-laden flows, in the movie I showed at the start, particles are actually moving. So now they don't have only a relative position, they also have a relative velocity. And you think about relative velocity, then you need to add 6 degrees of freedom per neighbor. So 3 components of the translational velocity, 3 components of the angular velocity. So we don't really fully know how to construct a model only with 3 degrees of freedom per neighbor. Now we have to construct a model with 9 degrees of freedom per neighbor. So honestly, I don't know how to do that. I don't even want to think about it, otherwise I'm going to have nightmares. The other thing is that I've been talking about transferring knowledge from the microscale to the mesoscale. And why that's doable with this type of model is because at the mesoscale, again, remember, I'm still tracking the position of each individual particle. So I actually know what the microstructure is. So I can use these models. When I move to the macro scale, I'm representing the dispersed phase, the particles, as a pseudo-continuous fluid, like another fluid phase. And I don't have the position of the particles anymore. So all these models I presented, you can't use them in microscale modeling. So the change of scale, how do you represent the microstructure at the macro scale is something that is fully open. And I think someone else has to look at that, because I don't want to start to look at this problem. I think it's far too complicated. But transferring from micro to meso, clearly the model I discussed here, they should normally perform reasonably well, and the future will tell us whether that's true or that's untrue. Okay, well, thank you very much.
Thank you, Anthony, for this very, very interesting talk. And now it's time for questions and comments. No, I will start with again. I mean, you explained a little bit about these models for the force for that.
Yeah.
But I'm curious about how to decide what of these models are the proper to use. I mean, it depends on the material, or I don't know.
No, so we assuming that the particles they're just rigid bodies. Okay, they have a density, but I mean, this is regardless of the density here, because the hydrodynamic force is only a function of the relative velocities, the Reynolds number, and the volume fraction. So the properties of the particles, the material properties of the particle, do not enter the hydrodynamic force and torque laws. So you don't really care. Of course, they shouldn't be porous, for instance, because if the material is really porous, then you have to add corrections to this hydrodynamic force and torque exerted on the particles. And there are models for porous particles, but that's, again, you adding more difficulty to trying to determine what these force and torques are. Yeah.
Okay. Another question regarding the data. You see the data used in training of the for the networks, the neural networks is produced
Yeah,
by simulation, right? But how
yeah.
do you produce the simulation? Solving some model before or something? Probably I missed that.
Yeah, so we running particle resolve simulations.
Okay.
So we take a cubic box, okay, the simplest configuration you can think about. So it's multi-periodic. You impose a pressure gradient. There's a flow with the average velocity. You get the Reynolds number. Because you have a certain number of particles in your box, you have an average volume fraction. So that determines the case: average Reynolds number, average volume fraction. And we solve the conservation equations on that system with an immersed boundary type of method, with fictitious domain, whatever. Then the output is the exact or almost exact, provided spatially converged, the exact forces and torques on each individual particles. And these are our data. And that's what we use later to construct the different models I talked about. Yeah.
Right. And sorry, probably this is very naive, but is it possible to get some data from the experiments?
Yeah,
I mean,
okay, sure. So you can get data from experiments.
I mean, real data,
Yeah,
let's say.
but that's sort of the advantage and the beauty of particle resolve simulations is that what we get from particle resolve simulation, experimentalists cannot measure it. They can't. They can create an experiment with multiple thousands of particles and track exactly the hydrodynamic force and torque exerted on each individual particle over time. They don't have the tools to do that. But particle resolve simulation can do that. So that's really why we're running millions of computing hours on supercomputers. Really, we want to get this data that experimentalists cannot get.
Okay, cool. Yeah, that's really interesting. I mean, this connection with this physics informed, I'm really, I have to admit I am an ignorant regarding that, but it looks like promising, I'd say.
Yeah,
Okay.
yeah.
Is there any more questions or comments? Okay, I think it's not the case. Well, Anthony, thank you again for this talk. Thank you for accepting our invitation. It was very nice to have you here, at least virtually. Hopefully, sometimes you can be here in person. You are always invited, of course. Sorry, there is one more question, I think. Sorry. For machine learning,
so
do you suggest some?
Yeah, so the machine learning models were developed on Python using that library that I have forgotten the name of, because that's what my PhD student did. Something like Kerak, or so just using online free resources to create the machine learning model. I think maybe also Google has a library that I don't remember the name of right now, but I mean, this is all over the web for free. Yeah, and it was developed in Python. And I think actually that you can. All right, let me just one second. My PhD student has, I think he has published that online for free, so you can even download his machine learning model. Let me just check if I can recover that quickly. It's in his paper, in the paper we published. So I can, let me just share my screen for 1 second, can answer that question. Okay, so this is a paper in Computers and Fluids from this year. So it's very recent. And somewhere, I think Arman said that the machine learning model are freely available. He has a Git repository. Don't remember where he said that. Otherwise, you can just download the paper and search.
Exactly. That's a good pretext to read the paper. So
yeah, so it's somewhere he's saying, oh, here, GitHub. So let's see. All right. So all the files are here. It's completely freely available.
Perfect.
Okay, so you can if you want to check that out, go ahead. It's free knowledge. So.
Perfect. Thank you, Anthony. Okay, once more, thanks for accepting the invitation.
Yeah.
As I said, you're always welcome here. Hopefully,
Sure.
you can come. It would
I'll
be
be
very
happy
nice to have
come.
you.
I came to Ecuador in 2004, doing some climbing on Chimborazo and Cotopaxi.
Cool.
But
I didn't know that.
I never had a chance to come back. So yeah, sure, I'll be happy to come and visit you anytime. Yeah, with my pleasure.
We have to create that chance for sure. Yeah. We will.
All right. Thank you very much,
everyone.
Thank you. For attending. It was my pleasure. Have a good day.
Thank you all.
Thank you.
Bye.
Thank you.
Thank you.
Have a good one.
Thank you.